Thousands of species have been introduced outside the natural ranges, but only a small subset of naturalized species become invasive. A central goal in invasion ecology has therefore focused on identifying characteristics of invasive species. This is important for conducting risk assessments prior to introduction, as well as prioritizing control efforts among newly introduced species. Factors such as efficient dispersal modes, large native range sizes, and large seed banks have been documented in model groups such as pines and Australian acacias. Araceae also serves as a model group, since this ancient monocot family has a long history of introduction to regions outside its natural range for use as food, as you can see in the first column, horticulture and medicinal purposes. Looking at the invasion continuum proposed by Blackburn et al., there are several barriers that non-native species must overcome in order to become successful invaders. Once introduced, species need to overcome survival barriers and form self-replacing populations in order to be naturalized, and these self-replacing populations need to spread great distances from the source population in order to become invasive. Therefore, it's important that each transition stage should be examined separately to identify drivers of invasiveness. The aims of my study were to first create a species inventory using databases and literature sources. The second aim was to describe the invasion status of all species using databases, some of which are shown here, literature sources, and expert opinion. Thirdly, several variables were analyzed using boosted regression trees to identify potential influential variables across the invasion stages. Here I built three models: an introduction model, a naturalization model, and an invasion model. And using these influential variables, I ran generalized learning models to provide a potential explanation of each variable. These traits included human usage, native range size, several biological traits, and data on the introduced range. And lastly, I look at a very important aspect in invasion ecology, which is predicting potentially invasive species. My approach here was to first select monophyletic groups using published phylogenies. This accounts for evolutionary relationships between the species, and the duckweeds is an example of this. Next, I scored species based on characters shown to be important in other groups. And using this matrix, I constructed a phenogram which is based on similarity of characters. Coming to the results, my final list included 3,494 species belonging to 115 genera. This includes 468 introduced but not yet naturalized species, of which 27 species are naturalized but not yet invasive, and 19 species are considered invasive. Plant life forms was one of the most important variables across all models. The first graph is the introduction model, the naturalization model, and the invasion model. Plant life form was especially important in the introduction model with chamephytes, which includes dwarf shrubs and similar forms, epiphytes, which includes vines, and hydrophytes, which includes aquatic herbs, being more likely to overcome the introduction barrier. These species are used in the horticultural shade for use as ornamental species in gardens, as well as in aquariums and ponds. The number of floristic regions was also an important variable in the boosted regression tree models. This was used as a proxy for native range size. And as you can see from the figure, species that occur over a larger area in their native range have a greater chance of being introduced and naturalized, but other factors come into play for invasion. The types of pollinators was another important factor in the introduction model, with species that are pollinated by a combination of pollinators such as generalist species being more likely to be introduced. However, there was no significant difference across the different invasion stages. The number of introduced regions